Welcome to this video on Euler's implicit method. By the end of this video, you will be able to solve an ODE using Euler's implicit method. Now, just as a reminder, our general solution technique for a first-order ODE was to calculate the new independent variable by adding a constant step size h, so xi plus 1 is equal to xi plus h, and calculating the new value of the dependent variable yi plus 1 by adding an average slope times the step size h to the known solution variable y sub I. And the trick was how to evaluate this integral that appears in the average slope formula. And we're going to use a numerical technique to do this. For Euler's explicit method, the forward Euler method, we used the rectangle method with the left bound, giving us the height of the rectangle. For Euler's implicit method, we will use the rectangle method with the right bound of the integral, giving us the height of the rectangle. So as before, the integral that we have to evaluate is of dy dx, but dy dx is equal to f of xy. So we have to evaluate the integral from xi to xi plus 1 of f of xy dx. We're using the rectangle method with the right bound, giving us the height of the rectangle. So that would be f, the integrand, evaluated at the upper bound of the integration at xi plus 1 and its corresponding value yi plus 1 times the width of the step size, or the width of the rectangle, which is xi plus 1 minus xi. If we're doing equally spaced points, that would be h. All right, so that means the slope would then be this integral divided by h. So it's f at xi plus 1 yi plus 1 times h, divided by the h, so the slope will be approximated by simply the function evaluated at f of xi plus 1 and yi plus 1. Good, let's plug this into the update formula. So that means that yi plus 1 is equal to the currently known value yi plus the function, the right-hand side of the ODE, evaluated at the new point xi plus 1, yi plus 1 times h. That is Euler's implicit method, derived using the rectangle method to approximate the integral in the average slope. But there's again another way to arrive at this equation using finite differences. So if we go back to the ODE, and I'm going to approximate the derivative dy dx using a finite difference formula, and in this case the backward finite difference formula, I can write dy dx as being equal to, well, where? At xi plus 1, yi plus 1, because I want to approximate this going backwards. So I start at my new value, xi plus 1, yi plus 1. Using backwards finite differences, that then is yi plus 1 minus yi divided by xi plus 1 minus xi. And that has to be equal to, well, first of all, the xi plus 1 minus xi. If we use constant spacing, that's equal to h. But that has to be now equal to the right-hand side evaluated at the same location. But the location where I evaluated the finite difference formula for the derivative was xi plus 1, yi plus 1. So I now have to evaluate the right-hand side at that same location. So f at xi plus 1, yi plus 1. Okay, let's solve this for yi plus 1 by multiplying by h and adding yi to both sides. And we get, again, the same formula for the Euler's implicit method. Now, because of the use of backward differences here in the derivation using finite differences, this method is also called backward Euler. Okay. Now there's one tiny slight problem with this, or challenge, right? Unless f, this right-hand side function, is linear or quadratic, I have to solve a nonlinear equation here to find out what yi plus 1 is. And if the f is linear or quadratic, I can easily do that. But if it's a much more complicated nonlinear function, I will have to do this numerically. Well, but that's not that big of a deal, right? It's simply a root finding that I have to do to find the solution yi plus 1 that I can do numerically. Now let's do a challenge question of how you would code Euler's backward method, or backward Euler, or the implicit Euler method. The question is the following code correct to solve the ODE, dy dx is equal to the sine of x times the cosine of y on the interval from 0 to 1 with a step size of h equal to 0.1 and an initial condition y at x equal to 0 is equal to 2, and we want to use the backward Euler method. So what this code does is it first defines the right-hand side function f as an anonymous function, just as the sine of x times the cosine of y. It defines the given step size of the problem h is equal to 0.1, and then it figures out how many steps do I need to do to go from x equal to 0 to x equal to 1. That's the interval that's given. That's just by doing the rounding of endpoint 1 minus start point divided by h. Now the rounding is necessary, right, because of finite precision that we have when we do these operations with double precision numbers, and the number of steps should be an integer, a whole number. Then with the linspace command, I can set the values of the independent variable equally spaced between 0 and 1 using n plus 1 points, right? That makes sense. And I'm going to pre-allocate a row vector of the solution variable y. I need n plus 1 points for that as well. And I can set the initial constraint that at the first point y of 1, so the first point x of 1 is 0 because of the linspace command, the y value is 2. Right? That's given in the problem as well. Now, the way this code proposes to solve the Euler's implicit method, backward Euler, is we do a loop over the required number of steps, uppercase n, saying that y at I plus 1, and shown here on the right is that update formula, that is backward Euler. So y at I plus 1 is equal to y of I plus h times the function evaluated at x of I plus 1 and y at I plus 1. Right? So it's a direct coding of this formula that we had just derived. So is this code correct to solve this ODE using backward Euler? Please make your choice. Okay, turns out that is not the right way to solve this ODE. And the problem is that when you code something, everything on the right-hand side of the equal sign must be known. But in this particular case, for the backward Euler method, we do not yet know what is the value of y at point I plus 1. That's what we're trying to figure out, right? So we can't use that unknown value on the right-hand side. In fact, if we use this code like here, it would just be 0 at that point, which would not be the correct solution at the point xi plus 1. So instead, we would have to code this using a root finding procedure. Okay, now back to our Euler's implicit method. Let's look at a geometric interpretation of this again. And the idea of Euler's implicit method is to approximate the slope, the average slope on the interval from xi to xi plus 1 by the slope at the right edge of the interval from xi to xi plus 1. So use the slope at xi plus 1, yi plus 1. That will be the approximation that we then use this slope at xi, yi to find the new solution variable xi plus 1 and yi plus 1. Okay, let's do an example on this. Again, we want to solve the ODE here. dy dx is equal to 1/10 x times y plus x. But now we're supposed to use Euler's implicit method. And the step size h is still equal to 1. And the interval on which we want to solve is from 0 to 3. So I'm going to start with the initial constraint, right? So the constraint is again x1 is equal to 0 and y1 is equal to 1. So at I equal to 1, x is equal to 0 and y is equal to 1. All right, so here is the the backward Euler, the implicit Euler method, right, is written out here. And I need to figure out what is f in this formula. Well, but that is simply here the right-hand side. So this would be my f of x and y. Just color this in a little bit, right? This here, that is the right-hand side of the ODE. That is my f of x and y. Okay, so let's use this and let's plug this into this formula over here and see what happens. So I have yi plus 1 is equal to y sub I plus f of xi plus 1, yi plus 1, so 1/10 xi plus 1 times yi plus 1 plus xi plus 1. That's my f of xi plus 1, yi plus 1, right? Times h. So if you look at this equation now here, you'll see that I want to solve for yi plus 1, but that appears there on the left-hand side, but also here on the right-hand side itself. So I have to do some algebraic manipulations on this equation to isolate yi plus 1 to one side, to get an explicit formula that tells me yi plus 1 is some function of xi and yi only, or xi plus 1 as well. So how would I do this? Well, let me bring all the yi plus 1 terms over to one side, to the left-hand side. So I have yi plus 1. And then over here I have 1/10 xi plus 1 times yi plus 1 times h. And I'm just going to bring this over to the left-hand side. So minus 1/10 xi plus 1 times yi plus 1 times h is equal to yi. And then I have left here plus xi plus 1 times h. So let's factor out yi plus 1 on the left-hand side. So yi plus 1 times 1 minus 1/10 times xi plus 1 times h is equal to yi plus xi plus 1 times h. So therefore, yi plus 1 is equal to yi plus xi plus 1 times h divided by 1 minus 1/10 times xi plus 1 times h. Okay, so that is my update formula. And I was fortunate enough that the right-hand side of the ODE is simple enough that I can find this analytical solution. I can do these algebraic manipulations to find out what is yi plus 1. If the right-hand side of the ODE is more complicated, well, then we'll have to use some numerical technique to find the root of this equation, this update equation here. But here we were able to find this formula. So let's jump in and do our work. So if I is equal to 1, then I have my x2 is equal to x1 plus h. So that's equal to 0 plus 1. That's equal to 1. So if I is 2, then x2 is 1. And my y2 is equal to, right, here is now the formula that I'm going to use. So it is y1 plus x2 times h divided by 1 minus 1/10 times x2 times h. Okay, let's plug in the values. Right, so let me mark where I'm going to take the values from. The y1 is this value over here. The x1 doesn't even appear in the formula. it's simply the x2 that appears. That's over here. That's these values. And the h is 1. Okay, so y1, that's 1 plus x2 is 1 times 1, h is 1, divided by 1 minus 1/10 times x2, that's 1, times h, that is 1 as well. Okay, so that's equal to 1 times 1 is 1 plus 1 is 2, divided by 1 times 1 divided by 10 is 0.1. 1 minus 0.1 is 0.9. So it's 2 divided by 0.9, that is 2.22 period. So the result would be here 2.22 period. Okay, I equal to 3. I equal to 2. Got ahead of myself there. I equal to 2. x3 is equal to x2 plus h. That's 1 plus 1 is equal to 2. So I is equal to 3, x is equal to 2. y3 is equal to y2 plus x3 times h divided by 1 minus 1/10 times x3 times h, which is simply this formula here applied to I being equal to 2. Okay, so let's plug in the values. Let's mark them first over here. So let's see. So I have a x3 that I have to use. That's this value here. And then I'll have a y2 value, that would be this value. Okay, so that's equal to 2.22 period plus x3 is 2 times h is 1 divided by 1 minus 1/10 times x3, that's the 2, times h, that's the 1. So let me just mark them where I got these values from. Those are the x values, that's the y value. And that would be 2 plus 2.22, so that's 4.22 period, divided by 1 minus, so 0.8. And that's equal to 5.277 period. 5.277 period. And then finally, for I equal to 3, we have x4 is equal to x3 plus h. That's 2 plus 1, that's equal to 3. That's I equal to 4. And the y4 is equal to y3 plus x4 times h divided by 1 minus 1/10 times x4 times h, which is equal to 5.277 period plus x4 is 3 times 1 divided by 1 minus 1/10 times x4 is 3 times 1. So that's equal to 8.277 period divided by 0.7, and that's equal to 11.8254, and so on. So 11.8254, and so on. And that's how we would solve Euler's implicit method by hand, going through the individual steps. And the key thing is to be able to solve this by hand is to be able to solve the general equation here for the new solution variable yi plus 1. And then it just is plugging in the appropriate values. Thank you for watching.